Hello everyone, good morning to everyone. And here I am going to demonstrate my project on ELP101. So let me share my screen. So my project is on Thevenin equivalent and Northern equivalent circuit. What is Thevenin theorem? Thevenin theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source V Thevenin in series with a resistor R Thevenin, where V Thevenin is the open circuit voltage at the terminals and R Thevenin is the input or equivalent resistance at the terminal where the independent sources are turned off. For the clear demonstration, I have taken an example for the solving of the Thevenin theorem. Uh, uh, Firstly, with no dependent source in the circuits. Here is the circuit diagram which I have used to demonstrate and converted it to, when it is converted to Thevenin voltage and resistance, it will look something like this. For doing so, firstly, we need to find RThevenin. And for RThevenin, firstly, we have to remove the load resistance, which is this given to ohm. Voltage source should be short circuited and the current source should be open circuited. After doing these all steps, the diagram of the circuit diagram will look as follows. And after solving the series and parallel registration combinations, firstly, 6 ohm and 6 ohm resistance are in series, so it's sum up to 12 ohm, and it is parallel with 4 ohm. And on doing that, we will get R Thevenin as 3 ohm. R Thevenin is 3 ohm. Okay. Secondly, to find the Thevenin voltage, we need to open circuit the load resistance, and the voltage Thevenin voltage is equals to open circuit voltage, which is the voltage across terminals A and V. By nodal analysis at node 1, which is this, 12 minus V1 by 6 plus 2 equals to V1 minus V2 by 6, and it gives V1 as 24 plus V2 by 2. It's our first equation. At node 2, here V1 minus V2 by 6 equal to V2 by 4, which also give V1 as 10 V2 by 4. From equation 1 and 2, we get 24 plus V2 by 2 equals to 10 V2 by 4, from where we get V2 as 6 volts and we get V1 as 15 volt. But V2 is the voltage across terminal A and B, which is our Thevenin voltage. So our Thevenin voltage is 6 volts. So at last, we need to find the current through the load resistance. For that, we need V Thevenin by R Thevenin plus load resistance, which is equals to 6 by 3 plus 2 equals to 6 by 5 equal to 1.2 ampere. Now we will be doing the Thevenin problem for the dependent sources. Means circuit containing dependent sources. For the it, I have taken this circuit, and for finding the Thevenin voltage, which is equals to voltage our open circuit, we will use KVL in outer loop, which is this. For that, plus 3i plus 5 pi plus 3i plus 5 pi minus V Thevenin minus 3i equals to 0. At Q, using Kirchhoff's law at Q, I1 plus 10 equals to I, which gives I1 as I minus 10, which is our equation 2. That implies when we put equation 2 in equation 1, we get 3I plus 5I minus 50 plus 3I equals to VThevenin, which also gave VThevenin equals to 11I minus 50. At node R, I1 equals to Vx by 4. So from equation 2, from here, I minus 10 equals to Vx by 4, Vx equals to 3I, which also gave I equals to 40 ampere. So VThevenin equals to 11I minus 50, where I equals to 40, which gives our VThevenin voltage as 390 volt. For RThevenin, we have to make current source open circuit and put a test volt of 1 volt across terminal A and B for applying KVL. RThevenin equals to 1 volt by I naught. We need to find I naught. Applying KVL at outer loop, plus 3I plus 5 minus 1 plus 3I equals to 0, which gives I equals to 1 by 11 ampere. So RThevenin equals to 1 volt by 1 by 44 equal to 44 ohm. RThevenin we get 44 ohm. Where we get this 1 by 44, it is equivalent to I naught. Where we can find I naught, how we can find I naught is by applying KCL at R, which is KCL at R here. So I equals to Vx by 4 plus I naught, which gives I naught equals to 1 by 44, and further by doing so we can find RThevenin. Now we come to the Norton's theorem. Norton's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source IN, which is Norton current, in parallel with the resistor Rn, which is Norton resistance. IN, Norton current, is the short circuit current through the terminal. Norton resistance is the input or equivalent resistance at a terminal where the independent sources are turned off. Here is the diagram which looks like Norton, which is demonstrated how Norton's circuits looks like. Now, relationship between Thevenin equivalent circuit and Norton equivalent circuit. Here is the diagram, which is equivalent circuit for Thevenin and for Norton. The relationship between them is Norton resistance equal to Thevenin resistance, and Norton current equals to Thevenin voltage by Thevenin resistance. Here we take an example to solve Norton theorem to a circuit. Use Norton theorem in a circuit. Firstly, for finding Norton resistance, we'll remove RL load resistance. Voltage source will be short circuited, current source will be open circuited. So the circuit diagram will look as follow, and we take this in series, which is sum up to 6 ohm, and these two will be in parallel, so R parallel is equal to 3 ohm. So Norton resistance is 3 ohm. Now, secondly, for finding Norton current, we will need to short circuit the load resistance and short circuit the Norton current. And the diagram will look as follow. Norton current equal to short circuit current. By nodal analysis, 15 minus V1, 15 minus V1 by 3 plus 4 equal to V1 by 3, which will give V1 as 27 by 2, which is equal to 13.5 volts. Now, Norton current equals to V1 by R, where V1 equals to 13.5, R equals to 3 ohm, which is give 4.5 ampere, where R is Norton current, Norton resistance, and we get Norton current as 4.5 ampere. Now if we can connect a load resistance across A and B terminal, then we can find the load current. For load current, the formula is northern resistance by northern resistance plus load resistance whole into northern current, which will give current load current as approximately 1.04 ampere. That's all from me. Thank you.